Okay, going to do some different numbering systems and change a base. One of the first things you'll have to do is convert numbers from one base to another. So basically, in computer science, you're going to be asked to know about base 2, which is called binary. Base 8, which is called octal. Base 10, which is what we always use, which is the decimal system. And lastly, base 16, which is called hexadecimal. Okay, so basically those 4 bases. Now, what it means for that means is, so let's use the one that we know, which is the decimal. We have 10 digits, base 10. They are 0 through 9. Okay, so once we get to the 10th number, we run out of digits. So what we do is we put a 1, 0, indicating we have 1 in the tens place, 0 in the ones place. The next number would be 11, and so forth. Okay, so like if you had the number 45, then that would be 4 times 10 to the first plus 5 times 10 to the 0, because 10 to the 0 is just 1. 5 times 1 is 5. 4 times 10 is 40. That's 45. Okay, so if you understand that, then all of the other base systems are going to work the same way. Okay, so if you go to base 2, there's only 2 digits, 0 and 1. Okay, so once you get to the to write 2, right, you have to basically look like 10, 1, 0, which represents a 1 in the twos place and a 0 in the ones place. Okay, the next number would be 1, 1, which represents 3. Then we run out of digits again, and 4 would be 1, 0, 0. Okay, so if you had way down the line here, let's say 1, 0, 0, 1, then this is the ones place, which would be 2 to the 0. This is 2 to the first, 2 to the second, 2 to the third, which, 1, 0, 0, 0 would be 8. So this is an 8 plus a 1, which is 9. So this is 9 in decimal. Okay, so 1001 would be equal to 9 in decimal, or base 10. Okay, and all of them work the same. So if you understand that concept, then it's easy to go from system to system. So base 8, you have the digits from 0 to 7. And once you get to 8, that's 1. This is 1 times 8 to the first plus 0 times 8 to the second. So that's just 8. 1, 0 is just 8. Okay, so same way, if you got a number, let's say 57, base 8, then if you wanted to convert that to decimal, that would be 5 times 8 to the first plus 7 times 8 to the 0, which is always the ones digit. So that would be 40 plus 7 to be 47. Okay, so that's how these different numbering systems work. And hexadecimal is no different, except we use the numbers from 0 to 9, which would give us 10 digits. We run out of numbers, so we use letters. It goes up to F. So this would basically be our 10, 11, 12, 13, 14, 15. There are 16 digits, 0 to F. And then once you get to 16, it would be 1, 0 again. Okay, so that's 16. And it acts the same as the other base systems, except you have these letters to account for digits. Okay, so if you had a, way down the line here, let's say you had a 9A2 in hexadecimal base 16, then, still same logic. This is 2 times 16 to the 0. A is basically our tens unit. So that's like 10 times 16 to the first. And 9 would be 9 times 16 to the second. And when we add those up, I don't know what 9 times 256 is, but once we add these, that would be our equivalent in decimal. Okay, so just one last thing, because again, as long as you understand this concept, then it's pretty much the same way every time to convert from different numbering systems. So let's say we had a 53 in base 8, and we wanted to go to binary, which would be base 2. Okay, now there are some different, I guess you could just say, quicker ways to do this, because base 2, base 8, and base 16 are all powers of 2. 10 is not, so the decimal's a little bit different. However, I'll just suggest that you convert one number to decimal, since we have a really good understanding of what it means to be base 10, and then convert it from base 10 to the other. Okay, so that's what I'll do here, and I'll just do one problem, and if you want some more, I can show you some more. So 53 base 8 would represent 5 times 8 to the first plus 3 times 8 to the 0. Now this is in decimal form. Okay, so this would be 40 plus 3, so it would be 43. 43 base 10. Okay, so if we wanted to go 43 to base 10, or 43 is base 10, we want to go to base 2, we want to convert it to binary. So the way that we would do that is we'd have to think in terms of powers of 2. So powers of 2, you could get a 35. You don't, which would be 2 to the 5th. Okay, you don't need a 2 to the 6th, because that would be 64, and 43 is bigger than, or smaller than that. So I need a 2 to the 5th, which is 32. 32 I need to account for another 11, because 32 I still need to get to 43. So I need another 11. So I would need an 8. I don't need any 16s, because 32 plus 16 would be 48. So I don't need any 16, so I do need a 2 to the 3rd, which is an 8. So this is 32, this is 8, that's 40. So then I need a 3. So then I don't need any 4s, because that would give me 44. I need a 2 to the 1st plus a 2 to the 0. Remember, this is just 1. Okay, so and how that would work out in binary is you just put 1s in the places where you needed a number there. So we have a 1 for 5, 0 for 4, a 1 for 3, a 0 for 2, a 1 for 1, and a 1 for 0. And this would be base 2, which would be the equivalent of 53 in base 8. Okay, and you could just think this is, if you did this, it would just, the way we originally did it, would just go back to this. This is 1 times 2 to the 0, plus 1 times 2 to the 1st, plus 1 times 2 to the 3rd, plus 1 times 2 to the 5th, which is this, which is 43, and then that is 53 base 8. So as long as you can do one problem, I think the same logic is going to apply to all the other ones, so you can do it like that.